How much fits inside? The edges are fractions. We will fill it.
Welcome to Mossback Stone Den. Watch the scene closely, because the math we are looking for is built directly into this environment. We know how to find the volume of a rectangular shape when the sides are whole numbers. Our challenge today is to figure out the volume when the edges of our shape are fractions. Notice how the beaver meticulously arranges these real logs and stones to form the skeletal frame of a new prism. Even though the edges of this structure are cut into fractions, the logic of measuring volume stays exactly the same. We are still finding the exact amount of three-dimensional space enclosed inside that frame. Let's look at this diagram showing the exact dimensions of the beaver's first frame. The logs give us a length of 1.5 units, a width of 1 unit, and a height of 1/2 unit. To work with these dimensions easily, we need to turn any mixed number into a proper fraction. So 1.5 becomes 3/2. From here, we can use the standard volume formula. Volume equals length times width times height. We take the physical dimensions and multiply them together. We multiply 3/2 by 1 by 1/2. That gives us a final volume of 3/4 of a cubic unit. Converting the mixed number into a fraction from the start is the step that allows the standard volume formula to work accurately.
Tiny cubes still count. Multiply length, width, height. Fractions play fair too.
This new diagram shows a different prism, measuring 1 by 3/4 by 1/2. Instead of just multiplying, we can also measure this space by packing it with tiny 1/4 unit cubes. Since the little cubes are 1/4 of a unit wide, exactly 4 of them will fit along the whole 1 unit length of our frame. Moving along the 3/4 unit width, we can fit exactly 3 cubes. That forms a complete base layer that is 4 cubes long by 3 cubes wide. These auxiliary blueprint marks show area patches, reinforcing how we map out flat grids before building upward. Given a height of 1/2 unit, pause the video and see if you can calculate how many 1/4 unit cubes will fit along that vertical edge to find the total number of cubes in the entire structure. Since a half is equal to 2/4, the 1/2 unit height holds 2 cubes. We multiply the 4 length cubes by the 3 width cubes by the 2 height cubes, giving us 24 tiny cubes total. Counting the physical volume of these tiny packed cubes calculates the three-dimensional space just as accurately as our multiplication formula. Let's check a final capstone diagram with edge lengths of 2/3, 3/2, and 2 units. We can apply the volume formula right away by multiplying the length, width, and height. Notice that 2/3 and 3/2 are reciprocal fractions. When you multiply them, they cancel each other out perfectly to equal 1. That leaves us with a final volume of exactly 2 cubic units. If we had decided to pack this exact space with matching fraction cubes instead, they would fill the exact same total space. Both methods lead to the identical result. Back here in the physical den, the finished solid structure sits securely in place, its space measured and confirmed. As we finish, take a look at the den around you. Which specific mark in the environment proves the mathematical relationship? And how did the animal's physical building action make it true?
The box is full. Volume is multiplication. Measure something small.